Welcome to Rudy's Electronics Lab. Recently I posted the first episode about what's going to be a series of videos about bit error testing, where we're looking at telecommunication systems and the question whether errors occur when data is being transmitted over these systems. And in that first episode already talked a little bit about the principles, and I announced that there are going to be further episodes when we're going to look at measuring equipment and build some of our own equipment along that line. But I also want to spend one shorter episode here looking at some of the sources of bit errors. And as already have noted in the previous videos, these sources are various. Sources of bits being received by error can be noise on the transmission channel. They can be interference, that other amplifiers are transmitting on the same frequency. There may be bit synchronization problems. There may be attenuation because the long distance between receiver and transmitter, basically the energy of the signal becomes relatively weak compared to the energy of noise. There might be nasty cases of multipath fading, where we got reflections to buildings and so the bits arrive on kind of different times. And on top of it, we might also have the problem of noise that comes from active components rather than the telecommunication channel itself. We might have errors that come from distortions on by the components. We might have distortion problems coming in because of non-linearity of components, etc., etc. So there are quite a lot of different sources, but the one that I want to specifically dig into today is noise, as one of the very common sources of bit errors in a system. And for today's episode, I want to basically be looking at three different types of telecommunication systems and see how noise affects their performance. So today I'm going to look at amplitude shift keying, a system in which only two different values are transmitted at any point in time. I want to look at phase shift keying, so a more complex system in which 1 out of 16 values are being transmitted at any point in time. And I want to go look at even more sophisticated system, a quadrature modulation system, 16QAM. And today I'm going to try to show the influence of noise on transmission error basically in a graphical form. So I'm going to use plots. And I'm not very good at drawing these plots by hand. They can be rather complicated three-dimensional plots. So what I'm basically going to do is use some computer software to generate these plots for us today. And I want to show you a little bit about the computer program I'm using for that. You get an idea how these plots are made, and I will also be sharing all of the code, so you can basically also run that code yourself. And the software I'm using here is Mathematic from Wolfram, and that is actually a pretty good platform for being able to visualize this type of distributions and values in plots. And to give you an idea, I just want to give you a demonstration, a live demonstration of two different plots that I'm going to make here. And then later on I'm going to use the same system for all the other plots and share the code on that. So let's open basically the window of Mathematica, and let's start basically to introduce some codes of some of the plots that I will be using here. And what we're doing here is starting off with making a plot, a graph of a transmission value, and then the noise, Gaussian noise, which is distributed around it. So that will be done by using a exponential function. So what we got here in Wolfram is actually we're going to set some parameters. We're going to ask him to plot a exponential function. Some of the parameters that we got over here, including a parameter that parameterizes the noise level, and then we got some other plot function here. It's still fairly simple what we see here, but with this simple thing we can basically already plot a function, as you can see here. Let me make it a little bit bigger, how the noise is distributed around the transmitted value. Yeah? And so the nice things about Mathematica that you can also do this type of plot for much more sophisticated type of situation. So I'm going to take some other code here and I'm going to bring that now into Mathematica. And okay, this might already look a little bit overwhelming, but this is even not that much code. We got a number of parameters here, and we got a plot function that plots a number of different values at the same time. And let me just execute it, because then we get an idea of what it does. There it goes, it's already executed. Let me make it larger. And what do we see here? We see a complete QAM16 signal in a three-dimensional space. So we see, and we can even play around with it the way that it's shown in the three-dimensional plane, and we see all the 16 different values that our QAM16 system can take, and around each of these values we see the noise being distributed in the three-dimensional way around each of these values, so we can see the where the overlap kind of occurs. So a very powerful piece of software that is very suitable for the type of exercise that we're going to do today. Kiku. And so now, without further ado, I want to go back to basically looking at the different type of telecommunication systems. And as I said, we're going to be starting with looking at amplitude shift keying. Just a simple system in which we're going to transmit either a bit 0 or a bit 1 in the system, represented by two different magnitudes in the system. And at the receiver side, to determine whether something is a 0 or 1 is fairly simple as well, because the only thing we need to do is to determine whether it's on the left of this red line or the right of this red line, because the values I've chosen here are symmetrical here for 0 and for 1 in relation to the 0 line. Okay, so let's take a look at how that signal looks like. So if we got a signal with no noise, then we would have two peaks, one for 0 and one for 1. And I'm plotting that right over here. Actually, what I'm plotting here is with a tiny little bit of noise, because with no noise it will be infinitively narrow, this line. So I already used the formula, the exponential formula that I just introduced basically, but the amount of noise being modeled here by the parameter A is very, very low. And there's no problem for the receiver at all to see something as a 0 or a 1, because there's no uncertainty, there's no noise that makes that more difficult. Right here I'm going to show you also the code for a moment that is used here, so it adds the color things in particular. Now let's add noise to it. So we're going to increase this parameter A, that parameterizes the noise here, to a value of 2.2, and we see both noise coming around the value representing bit 0 and noise around the value representing bit 1. And the problem that we're going to have here, of course, in this overlapping regions around 0, where wrong decisions are being taken. So let's zoom in, do it a little bit more, and let's look at the bit 1 signal. So basically it goes wrong when the bit 1 signal is being transmitted, but by error, because of the noise, the receiver gets something below 0 and thinks it's a bit 0, 1, or the other way around, where a 0 is being transmitted and the receiver thinks it's a 1. So what is the likelihood, what is the chance in this system that a bit error occurs? Well, we can describe that chance as the part that is shaded here in red, where the bit error occurs, compared to basically the volume, the surface where the bit value is correct, so which is the green area here. So this is simply the situation in an ASK system with only two values. But now, of course, we want to look at a bit more sophisticated types of telecommunication systems, and we're going to move to the 16 phase shift keying system. So 16 different values can be transmitted at any point in time, which means that we can actually code 4 bits at the same time. We can transmit 4 bits at the same time. Now, the interesting thing about this system is that all of these different values are located on a circle, and so the amplitude of the signal is going to be always the same. And that is an attractive property, because that means that we can use very simple transmitters in such a telecommunication system, because they don't have to meet much of linearity type of requirements or so, because the amplitude for any value is going to be the same anyway. So this is a rather popular type of modulation system, because it's low requirements on the equipment. Now let's take a look how noise affects the working of this system. So also here the receiver has to determine where a certain value is. Is it the dot on the right here representing 0, 0, 0, 0, or is it the dot over here representing 1, 0, 0? So the transmitter will have a threshold exactly between these two values. And if we plot that, and I'm going to use Mathematic for that, again, these are the threshold values. So one of the dots is going to be here, one of the dots is going to be right there, and right between this is the threshold value. Now let's go and turn the telecom system on. Let's transmit some signals. Let's start signals without noise, and what we see here is basically very sharp spikes, perfect signal, very, very little noise. Still drawing a little bit of noise to make them visible in the first place, so they're not infinitively small. But here the receiver will have no problem whatsoever to see which of the 16 values is being transmitted. There's going to be hardly any transmission errors. Now I'm going to increase the amount of noise, and I'm going to increase this parameter A by the same value as I did it for the example of ASCII I had before. And what we get there is like a total mess. What we get here is a telecommunication in which the receiver can hardly see anymore which of the proper values is being received over there. And it's kind of better, easier to understand this if we just look at one single signal and not at all of the 16 signals again at the same time. So let's pick out one of the signals, and I'm shading the part here where the signal is properly within the threshold values where it should be between the two red lines in question. I'm shading that in yellow. And the other part is shaded in orange. And all the positive surface here in orange here basically is error. So there's a very significant amount of errors taking place in this system. How can we improve the system? Yeah, for this system to work we really need to make sure there's less noise. So I'm here reducing the noise parameter to only about half of that value, and then we get to a situation where we can still reasonably identify the different values, the different spikes apart from each other. There's still some noise here, so this is not a system without any errors, but hopefully the error coding or the robustness against errors is good enough basically to make this a workable type of system. Now I want to move now to a more advanced quadrature modulation system. So here systems are being transmitted with both an I component and a Q component coded in quadrature, and so we have 4 distinct values along the I value and 4 distinct values along the Q, so we have 16 combinations total. So also here, like in the previous one, we can send 1 out of 16 values at any point in time, and like in the previous one, that means that we can transmit 4 bits at the same time in this system. Now let's look what that means for noise, and again we start by looking at where are the threshold values for the transmitter. So if we look at this, we could basically draw the quadrants in this system that would look a little bit like that. But of course we don't have to see if the value is higher than a certain point. We only need to see the threshold in between the values. So actually the grid over here is more than enough. We have 3 threshold values on the I axis, and we have 3 threshold values basically on the Q axis. And now we're going to turn again on our system and see how the signal comes in. And again, if it's a very clean signal, no noise, there's going to be sharp spikes and there's going to be no errors at all. The receiver can perfectly see which out of the 16 signals is being transmitted at a certain point in time. Now adding noise again, the same noise that I did for the other examples, parameter value 2.2, and also we see here of course a landscape in which there's going to be a bit more overlap, so the bit error is increasing here, and again we can look at one particular value here and how it's affected by noise. And we can isolate that one, we see only that one. And again here the yellow one, that are the good measurements by the receiver, so it's exactly within the red threshold lines, while the orange one here basically, those are the ones where errors do occur. So we see some errors, but we see less errors than in the phase shift keying scheme. Actually we can prepare those 2 different schemes here. On the left hand side you got 16 PSK, on the right hand side you got 16 QAM, and what you see here basically is that the phase shifting system performs considerably worse. It's harder to see the values apart from each other, And why is that the case? Even though both systems can transmit 16 different signals at any point in time, in the PSK system they're all aligned on a circle, which means that these points are relatively closer together, while in the QAM system these 16 points are more spread out over space via this more matrix. So that basically means they're further apart from each other, and it's easier basically to distinguish which of the ones they are. In other words, if we look at the lower part of the picture, we see also that the amount of surface that is not yellow basically is larger in the phase shift keying system than it is in the QAM system. Okay, that brings me to the end of this shorter episode. I hope this gave a little bit of an idea about bit errors that are the result of noise in the telecommunication system. And in the upcoming episode, we're going to look more at ways to measure bit error rates and also ways to generate test signals. And we're also going to look at a little project where we can build a test signal generator ourselves. And that's, I think, the more exciting part of it. But I hope this part was useful to have more an understanding of noise on a telecommunication system. See you again on a next episode, I hope. Thanks.